Good morning, small class. How are you? Weekend? Ready for a weekend? If I didn't get your exam back to you yet, I will walk around as we're working on stuff today, and I will get your exam back to you. If you don't get it before the end of class, come see me right before you leave, and I will hand it back to you. So we have a first question up here that I want you guys working on if you have not already. So try to find someone around you to start working through this with. What do we have to do before we can answer the flicker question? Alright, so go ahead and work on balancing this equation. I'll give you guys about a minute to work on balancing, and then we'll talk about the second part of this.
I'm not smart, so I'm not going to say what I got. Because whatever it is, it's wrong.
They're burning 6 molecules of gas. That's going to go up as well. Oh, you're fine. You did the same thing. You can just... You're fine.
So there are 3 then.
Well, they're burning 6 molecules of propane though.
Alright, everybody.
And there's a coefficient of 1.
Let's go ahead and talk through this. What are approaches you guys use for balancing equations? Can someone raise their hand and talk about the approach used, DeAndre?
I start like with one atom. Like I start with carbon first.
One element? Yeah.
Or hydrogen. I see hydrogen has 8 on one side, so I put a 4 in front of the 8 on the other side.
Okay, and I'll add that I absolutely agree, and I would always usually save hydrogen for last. And the reason is a lot of times you have, those are the easiest to manipulate, so you can kind of move those around. In this case, the one we actually might do last is oxygen, because we can change the number of oxygens on the right side without messing with anything on the left side. So if you did carbon first, what would you do for balancing that? Thanks, Josh. Okay, so I love where you're going with this. So the first thing is if we balance carbon, we have 3 CO2s. But then you notice in water, there's an odd number of oxygens. You can't have an odd number when the only source of oxygen is these 2 from an oxygen molecule, right? There's no way to take this and make 1. So that might be a good reason to put some multiple of 2 over there for water. And so how did you determine what multiple of 2 to put for water?
I just put a 2 in front of C3H8, and so I put an 8 in front of H2O8. So then it's 16 hydrogens and all.
So if we do 2 molecules of propane, that would make 6 CO2s. And then on the left side, we have 16 hydrogen atoms. So So on the right side, we need to make 16 hydrogen atoms. Just so we're all on the same page with terminology, that number in front of the molecule saying how many of them we have, that's called the coefficient. Stoichiometric coefficient. All right? Are we done? Are we balanced?
No.
What are we missing? 6 molecules of propane. Well, so the thing that's not yet balanced, if we look, and sometimes it's nice to make a table, how many carbons, hydrogens, and oxygens you have on each side to check your work. So on the left side, how many carbons do we have?
6.
How many hydrogens?
16.
And we have 2 oxygens. On the right side, we have 6 carbons. We have 16 hydrogens. And how many oxygens do we have?
20.
So we have 6 CO2s. Each one of those has 2 oxygens, so that's 12 oxygens. And then over here, we have 8 more oxygens. Are we balanced? So balancing, I know that your book and everywhere describes it usually as like accounting. That's one way to think about it, the mathematical way. I also want you thinking about, can we create 18 oxygens in the process of this reaction? It's a chemical reaction, we're not going to create any oxygens. So how many more O2s do we need?
10.
So let's go ahead and change our stoichiometric coefficient to 10 there, which then means that we will have 20 oxygens on the left side, and the nice thing is that didn't influence the number of hydrogens or carbons. Manu?
Yeah, simple.
So let's do that. What would the simplified version of this reaction be?
5, 3, 4.
Okay? The reason I worked it out that way is because if that's the way that your mind works, if you wanted to start with 2 of the propanes, totally fine, as long as you get a balanced equation. But the last thing you have to do is what Manu suggested. If we don't simplify it, then that is not actually the most appropriate way to describe that reaction. We want to say, what's the lowest whole number ratio between the molecules that allows us to say that we started with a certain number of carbons, we end with the same number of carbons. So a lot of this guess and check can work. It takes a lot longer. So practicing is very valuable because when you have to do it in class, we want it to be quick and efficient. When we're doing it on an exam, we want it to be quick and efficient. All right? Any questions on our balanced reaction? Let's put in a sentence. I want you to put in a sentence So talk to your neighbor. Here's a sentence. I want you to describe what we just found out, the balance of the equation. I want you to use that to make this sentence. And see what other sentences you can make that relate those stoichiometric coefficients to each other. Can you guys read it? Make sure you've said at least one more sentence than this. What's another relationship we can use the stoichiometric coefficients to say about the relationship between reactants and reactants, reactants and products, products and products? You guys are super quiet today.
We did.
Okay. As some wise person said this morning, it's Friday, you can smile today.
Thank you.
All right, I'm going to hear from a few random people. I want to hear from Taylor. Are you willing to take a stab at this? You want to pass? Kayla, I want you to try to put together, do this sentence for now, and then we can choose some other ones.
For every one molecule of propane, you make 3 molecules of CO2.
Great. Did anyone else have a different set of numbers here? Sarah?
You can do 6 molecules
Nice and loud.
of propane. You can do 6 molecules of propane and you can make 18 molecules of CO2.
You guys hear that? Okay, Joey.
Wouldn't you have to redo that and say fully? Or,
What do you mean?
I mean, yeah, you can make it, but that's if you have 5 oxygens. If you don't have 5 oxygens, then you can't fully do it.
So there's a caveat that I like to add, and this is the first time I've had a student beat me to it, which is fantastic. So one thing is the can is a qualifier, but then I like to add at most. Because that statement is only true if we have the right ratio of oxygens, or more oxygens. As long as that gas, that propane, is our limiting reagent, those statements are true. To a certain extent. In second semester, we're going to talk a lot about equilibrium. We show this arrow that goes one direction. In second semester, we're going to talk a lot about there's a lot of reactions that don't go to completion. That those reactants will actually come back together and form, the products will come back together and form reactants. And so that balance of the reaction going forwards and backwards means that this at most becomes really important when we talk in second semester. All right, did anyone have this statement for another relationship in the equation? Another stoichiometric relationship? Sam, what did you have? Okay. Come on, help me out. Do another relationship. Ruby?
For every molecule of propane, we can make 4 molecules of H2O.
Great. So looking at the relationship between propane and water. For every 1 molecule of propane we use, we can make at most 4 molecules of water. What's another relationship? Matt.
For every 1 propane, you need 5 O2s.
Okay. And I might specify for every 1 molecule of propane, we need 5 molecules of oxygen. Or we could also say for every 1 mole of propane, we need 5 moles of oxygen. Josh?
Is the limiting, actually I don't want to say limiting reagent, is the limiting number always going to be an odd one? So when there's an odd number, you're kind of like, all right, we're set.
You talking about when you're balancing? Yeah, so when you're balancing, looking for odd is going to be really important. If you only have even on one side, so oxygens are going to be required to be even because there's an even on one side. If there's odd on both sides, that's not necessarily the case. So if we had methanol, which is CH3OH, stop. So this is a fuel. You can burn methanol. You can burn ethanol as well. And so if this was our fuel, then there would be an odd number of oxygens on the left side, and then it becomes a little bit more complicated because you don't have that rule right away. Good observation. Yes?
For every n molecules of propane, we can at most make 3 n molecules of CO2.
Fantastic. So no matter what the proportion is, or what the number is, we can use that same proportion. And so I really want you thinking about the proportions. And so that n is an example of that it's a multiple of those. So then if we look at this kind of question, how many molecules of CO2 are produced when we burn 6 molecules of propane? I think Ruby answered that question, right?
No, Sarah didn't.
Oh. Did you do this exact one?
Yes.
Okay. So can you guys answer this question? You feel comfortable with this question? Let's do some more complicated ones, all right? So before we get into the other questions I have for today, I wanted to bring it back to the activity we did last class. I think that's going to be a really good study tool. There's a lot of practice where it kind of gets does some of the sentences like we just did, and then it relates it back to climate change. Maybe we can just spend a minute on this. How does conservation of mass that we're talking about, right, balancing of equations, how does that relate to the carbon cycle and climate change? I want you to talk to your neighbor for a second. How does the carbon cycle relate to balancing of equations that we're doing now? All right, I'm going to call in some random people, so make sure you talk to a neighbor and have some ideas on how to answer this, please.
That's what I'm thinking, but much more than that, it's just basically a relationship between methane and gas.
All right. I want to hear from. Let's hear from Kyle.
Okay, so in balancing equations, we want to account for the mass somewhere of the molecules. So in the carbon cycle and climate change, the carbon always has to be somewhere, and we have to account for it. It's kind of
Okay, so what are the different places carbon can be?
in the ocean.
Great. So carbon can dissolve the CO2 in the ocean, become carbonate, forms limestone. There's a whole cycle there, right? Where else do we find carbon? In the atmosphere, in what form? Mostly carbon dioxide. Okay. What about on land? What are the main places that we find carbon there? In trees and somewhat in humans as well. What form is carbon? What's carbon attached to in trees? What's the main molecule that we find carbon in? What's that? Glucose, and then that's built into cellulose, which is multiple glucose attached together. Okay, so that's what makes up the bulk of the mass of a tree. When trees die, or animals eat trees and then animals die, they become part of the surface of the earth. If they sit around under long enough pressure and temperature, they get converted to fossil fuels. So then, how does that relate to climate change? There's obviously only a set amount of carbon here. Carbon's either going to be up in the air, it's going to be in the land, it's going to be in the ocean, or it's going to be underground. It's only one of those places, that's all it can be. Unless we shoot a slingshot into space and fire some of it outside of our little biosphere. So then why does that relate to human impact on the climate?
Does that have something to do with like how many carbons each reaction that's occurring like in nature would take? Like if we're breathing, how many carbons we would exhale compared to how much oxygen we intake? Or if like it's plants, how much carbon they intake and like let off oxygen?
Yeah, I like where you're getting. So what you're getting at is the balance, right? If it's a cycle, if plants to grow take in CO2, so that means they're pulling CO2, so that means there's less CO2 in the air if plants grow. But then how do we release that back into the air?
When we burn fossil fuels and we're conserving the amount of carbon atoms in the entire Earth's biosphere.
So for all the plants and animals to become fossil fuels, it took a few million years. How long does it take us to burn those fossil fuels and release them back into the atmosphere?
Probably about a few hundred years at most.
Yeah, a few hundred years. We're not going to burn all the fossil fuels. We're not going to probably run out of fossil fuels anytime soon. But what we're doing is we're taking a process that Mohib was getting at. It's a process of that CO2 is being pulled into non-gas forms, and then we're burning a lot of those things or respiring. Right? When we breathe, we release a little bit of CO2. It's pretty negligible compared to everything else that's going on. But that means that there's a flux of CO2 going, carbon going into CO2 and carbon going into other forms. So why does it matter? We're increasing the amount of CO2 in the atmosphere. We're burning things at a much faster rate. Not only burning fossil fuels, we're burning plants. We're clear-cutting forests. We're burning down tons and tons and tons of, well, millions of acres of forest.
What would otherwise be a carbon sink?
What would otherwise be a carbon sink? So what happens? Why does that matter? Why does it matter that we have more CO2 in the air?
We have no way to take it out as fast as we're putting it in.
Okay, so it's getting more and more concentrated. And if you go to NASA's climate website, there's a live graph of what's happening. And it's, I think we talked about it on day one, but in the history of the planet, as far as we can go back, 800,000 years, it's never gotten above 300 parts per million, which is a form of concentration. It's now at about 410, and it's skyrocketing up. So why does it matter? Who cares if we have CO2 in the air? It helps plants grow, right?
It does, but
So what are the bad things about it? I want to hear from your voice. Diana.
Warmer water means all of the fish that we like to eat have parasites.
You skipped a step though. Why is there warmer water?
Global warming.
Why?
Because of pollution.
So how is it that carbon dioxide influences the temperature?
I got a different question, but at some point the Earth was just lava and CO2.
Yeah. Great place for humans to live.
Yeah, well, we don't need to live here.
Yeah, so actually,
We don't need to live here.
totally true. I had someone argue with me the other day, who cares what's going to happen because the Earth will survive.
Yes.
Totally true. The question is, do we want to be part of that?
The heat increase, okay, I might have this confused in my head in this exact moment, but in the atmosphere, with there being more greenhouse gases such as CO2 in the air, it makes it so that heat can escape from the atmosphere so it stays within our...
Close. I think you might have said it flipped. So if you think about on a really hot day, we don't have many of those here right in Arkansas. Is your car warmer than outside, or is it the other way around?
it's generally warmer.
Cars typically a lot hotter than outside, and that's because glass lets the sun's rays through, but the heat waves, the infrared radiation doesn't escape through the glass. So that means that heat gets trapped inside your car, but the light comes through. And CO2 is the same way. CO2 allows light to pass through from the sun, but once that hits the earth and is released as heat, that heat gets trapped. The thicker, the more CO2 concentration we have in the atmosphere. And so we've actually increased it 33%. It's pretty significant, right? So thinking about what that's going to do to our climate, and now we no longer call it global warming, because it's not just about temperature. If we have warmer temperatures, we have more evaporation of water, which means we have more drought in some places, but then we have a lot more water in the clouds, we have a lot stronger storms because the oceans are warmer, we have a lot more rain in certain places, so we have more flooding, so it's about climate change as a whole. Quick question, statement?
Yes.
Quick.
For starters, it might actually make some areas colder because some areas, like Europe, are heated by ocean currents that are going away because of climate change, as it turns out. So some areas may actually end up getting colder.
Yeah, and so people say in their microcosm, hey, it's cold here today, of course climate change isn't happening. If we step out and we look at the global perspective, that's going to be much more important.
It's not true. That is not true.
The counterpoint to that, though, is yes, it's colder, but it tends to be that I'm from somewhere where it snows a lot normally, and there has been a lot more snow recently because you do have more water up in those clouds, which when there is a cold temperature does turn to snow, and higher amounts of snow do accumulate.
Yeah,
that's all true.
So I think going back to Joey's point, Joey said that we don't have ways to take in that CO2. And I think that what's interesting is there's physically what's happening, and then there's political action on that. And so the thing that becomes very frustrating as a scientist is seeing the data, seeing the changes happen, seeing changes actually happen more quickly than predicted, more better, is that the political solutions are not being discussed or are being downplayed. So politics should be not about what is the scientific data saying, right? That's what the scientists say. Political side should be, okay, what do we do about the political or the scientific data? How should we act? And I think there's a lot of disagreement on how to do that, or if we should do anything. And so that's something that I think we, as citizens, need to probably get more involved with. All right, so anyway, I just wanted to make sure to tie in climate change to carbon cycle, to balancing of equations. The more we think about chemistry as here is an atom, what is that atom going to do? What is it connected to? Where does it go? It doesn't disappear. It's going to make a lot of our calculations easier. So today, I want you to be able to identify combustion reaction, describe common properties of those reactions. We're also going to work on balancing equations, of course, predicting theoretical yield, and then calculate the amount of reactants needed in order to get to a certain amount of products. So go ahead and balance our second equation on our worksheet for today, if you have not already done so. And then try to make some sentences like we did earlier about the relationship between reactants and products.
As long as we're not burning that carbon. Oh my God. Everything's on fire.
All right, we only got 14 clicks. Raise your hand if you're having trouble balancing. I can come around and help out. Balance out of my coffee.
Balance the coffee.
No, like her and I, the more you know us, and we feel like and at the end of that, we're like, love you tonight. The dysfunctional.
45.
All right, we've got 43 clicks. That means we're pretty much there. Wait on. So working through balancing, what atom did you add any coefficients to start before you balanced? So I was just talking through this, and for me, like we mentioned, since oxygen has an odd number, we know it has to be an even number. I would start by putting a 2 there for the number of waters, and then we can go back and we can change that. Is this good to do in pen, by the way? No. Don't do stoichiometry in pen. It's a terrible idea. Okay, and then we look at what element next? Where'd you guys go?
I just went straight to carbon.
Yeah, I would probably do carbon too. So we know we have 4 carbons in butane, so we're going to have 4 CO2 molecules. I hope that when you're doing this, as well as doing the math, you're saying in your head, if I start with 1 molecule of butane, I will have to account for all those carbons. Those carbons can only be one product, so that's why we have 4 carbons. It's not just math of like 4 and 4, right? It actually tells us something about where that carbon goes. If we do that, does everything look balanced? So we have 2 oxygens plus 8 oxygens, but our number of hydrogens are off, right?
Yeah, it's like way off.
So what do we do with the number of waters?
We need to increase that to 5.
Does 5 sound good to you guys?
Another problem.
Okay.
That gives us another problem.
What's that?
Oxygen in the air is O2, not atomic oxygen.
So we end up with an odd number again.
So we end up with an odd number. So we need to double everything.
Yes! Okay. And if we have 10 waters, that means that we had to have how many butanes?
2. Well, 2.
Because we have 20 hydrogens on the right. So as you guys see, if you feel uncomfortable doing this to start with, it's okay. It's an iterative process. We kind of go and we do a change and then we check. What does that mean for everything else? And then we do another change and we check. What did that do for everything else? And we kind of go through step by step. All right, and sometimes we can just see that. Once we've done enough practice, you might be able to look over here and be like, well, this needs to be even, but there needs to be a multiple of 10. So then we can do that as 5 or 10 water molecules. Okay? What do we end up doing with our CO2s then?
Double that.
So we have 2 butanes. That means that we end up making 8 carbon dioxides. And Angel, how many oxygens would we need to balance this equation? Oxygen molecules. So on the right side we have 10 oxygens here. And we have 16 oxygens here. A total of 26 oxygens. So how many O2s do we need? How many? Sounds good. That was like a balanced equation. Can we simplify it?
No, because 13 is a prime number. You can't divide that by anything but itself.
All right. So we have got a balanced equation. So now we can answer the bottom one. How many moles of water are produced when you burn 12 moles of butane? So what I want to do is, guess what kind of analysis we're going to do here? Dimensional analysis. Yeah.
Shocker.
All right. So if you haven't already done so, use this balanced equation to write out, using dimensional analysis, this question. What's our starting quantity? What's our ending quantity? What conversion factors do we have? Hint, conversion factors are embedded in this balanced equation. Make sure you write it out as dimensional analysis. I want to see everyone doing this.
So
you have another.
on the test, we have to do as dimensional analysis, or can we not just like,
This one you could probably just answer if it's a multiple choice, but I want to see everything fully worked out. And for now, we're going to practice working everything out. We're going to use class time for it. I want to see you do it.
Why wouldn't you do it the other way too? Doesn't make sense to me. I really miss on
So let's work through this together, because I hear some people kind of getting a little sidetracked. Heated might be a good word. Okay? What's our starting quantity for this calculation? Taylor? Sorry, eraser doesn't work so well. We're going to write that over 1. And then what conversion factors do we have available to us to answer, to get to the, well, we should probably say, what's the bookend? What's the final unit we're trying to get to? Moles of water, H2O. And what conversion factors do we have to use to get there? Taylor, you want to keep going?
For every 2 moles of butane, we have 2 moles of water.
Almost. Instead of we have, what would be a better word to use?
I think juice.
Yeah, awesome. So for every 2 moles of butane, we produce 10 moles of water. That is one of the many conversion factors we have available to us here. We were saying before, for every 2 moles of butane we consume, we also need to use 13 moles of oxygen. For every 2 moles of butane we use, we produce 8 moles of carbon dioxide. Right? You can do that for any of the relationships that you want in this. Now we have a ton of conversion factors available to us. So the reason I'm forcing you to do it this way is because I want you to take that mathematical equation, turn it into a sentence, then use that sentence in order to convert any way you want. So we don't really mind that this simplifies down to a smaller fraction. That's fine. But what we're going to see is that we're converting from moles of butane used to moles of water that we could possibly produce, the most we can. All right, so what do we find mathematically for that? 60. Questions on how we set that up? All right, if I'd given you grams to start with, grams of butane, could you have done this calculation? What would be different? We need to go from molar mass, how much, to convert from how much it weighs to find the number of moles. I wouldn't have given you that. All right, so let's try that. I think that is the next one that we have. So let's go ahead and talk about octane. This is when you talk about gasoline. This is one of the many components, but kind of what, if you simplify what gasoline is, we say it's octane-ish. So balance this equation, and then we're going to try to do the calculations below. Raise your hand if you want some help. Try to ask people around you, and then raise your hand. I'll be happy to come help. All right. You guys ready to talk through this one? Get moving. Let's talk about the balancing first. Let's make sure we're all on the same page with balancing. Can I have a volunteer for the balance equation? Go ahead, Mohammed. So why do we have trouble balancing it again? What's the problem with having a 9 beside water? So we'd have an odd number of oxygens on the right. We can't do that on the left.
Yeah, exactly. So I tried by going like the next number up, it would be 18.
Which means we need 2 octanes. And then what else do we have for coefficients? Well, careful, because we don't have CO2 yet. How many carbon dioxides do we make if we use 2 octanes? We would make 16 carbon dioxides because every octane has 8 carbon atoms. Every carbon atom has to be accounted for on the other side. And then I think I saw 25 for oxygen. Does that sound reasonable? Can we simplify this? Okay. You might have done double this, and you might have ended up with 450, 32, and 36. Totally fine as long as you simplify at the end. Okay? So then now, if we just take this question at the bottom and we try to figure it out, should we do it in our heads? No. Okay? What are our bookends? What's our starting quantity? And what's our final unit we want to get to? 3.5 moles of octane. And then we want to get to a final unit of? So over here we need grams of CO2. All right, what conversion factors do we have? Sarah, nice and loud.
For 2 moles of octane, there's 16 moles of CO2 produced.
Great. So I like the focusing on for every 2 moles of octane we consume, we can produce at most 16 moles of CO2. Are we done? We answered a question. This question, though, wasn't the one that was asked. This one stops at how many of them. Then how much do they weigh? Natalie, how do we figure out how much they weigh in grams?
I went to 1 mole of CO2 is equal to 44.0095 grams of CO2.
Great. So let's go through what each conversion did. If we talk about this first conversion factor, what did we convert between? Units of what and units of what? And the units I'm talking about are, there's no chalk. I always want us thinking, is it mass? Is it quantity? Is it volume? Is it length? So can I get someone to describe that first conversion? What did we convert between?
Quantities.
Can I get a hand raised? Kevin?
Quantity.
Great. We converted from quantity of a reactant in moles to quantity of a product in moles. What is the second conversion? What was that going between? Kayla?
Quantity to mass.
Okay, and even more specifically, quantity in what unit? Quantity in moles to mass in grams. Great. And we can do the calculation. I'm not too worried about the numbers. All right, let's do the last question. The last question is based on the same balanced equation. And by the way, did we, in the last one, what does it mean when I said it was in the open air? Why did I specify that?
Definitely in excess of oxygen.
We have plenty of oxygen. We're not going to run out of the oxygen at all. So if we then, we can think about the equation. If we had a specific amount of oxygen, that would change the way we might do our reactions. So go ahead and answer this next question. I'll do this as a new clicker. We have the balanced equation, right? It was what, 2, 25, 16?
Yeah, 16, So how do we put the Thompson handle, whatever thing on there? He wants that.
I'm not sure. I've never done it with these clickers. I've done it with the old candy bar
So I
style.
tried doing it, and it gave me a completely different answer.
So then think about how you would write it out to specify.
Right at the moment. We can look at the numbers there, that's possible.
So think about where you stop specifying significance. Yeah, capital E is times 10 to the.
So either
E or times 10 to the. E specifies times 10 to the. Raise your hand if you'd like any input. All right, we're running out of time. What's our starting quantity in this one? Matthew, you wanna? Do you want to talk me through this?
75.3 grams of octane.
75.3 grams of octane. Is our starting quantity?
That's number one.
All right, Jason, next up. Eric? What conversion factor do we use? Can we just use this ratio now? The ratio we had, right, was 2 to 18?
So we can't use it without conversion.
All right, so first we have to convert to moles.
1 mole.
Come on, help me out.
114.15092 grams, and then 1 mole on top.
And we need to specify, this is really important, specify grams of what, because we need to make sure the grams cancel out, because there's going to be grams of everything, there's going to be moles of everything, and that's 1 mole of octane.
Then we do conversion of balance equation.
And we know that for every 2 moles of octane, we produce, what, 18 moles of water. What's that?
Are we allowed to simplify that? Do 1?
Sure. As long as the ratio holds true, you're fine. And then in the end, are we done? We know that 1 mole of water weighs, what, 18.0 grams of water. So I had some people talking about sig figs. How many sig figs should our answer have? 3. The only number that has limited sig figs is our first one. It's all multiplication and division, so we would do 3 sig figs. Our answer should be 3 sig figs. Think about that for the previous one as well. So if we have a fire, what's the easiest way to put it out? We get rid of all the... We get rid of the fuel?
No.
It's hard to get rid of the fuel, so we can smother a fire. We make that the limiting reagent, and then the fire goes out, the reaction's done. All right, next class we'll spend doing some more calculations and stuff with limiting reagents. Homework shouldn't be too bad. Post questions to the blackboard if you have any questions. I can't think of a good way besides emailing it, yeah. Well, the problem is that this doesn't have what's wrong. It just has your answer.